Okay, hi everyone. Thanks, Ahmed, for the invitation. So, my name is Corentin Segalas. I'm currently a postdoc research fellow at Bordeaux Population Health, which is a public health research center attached to the University of Bordeaux. And I'm attached to the biostatistics team. So, in this team, we are mainly working with longitudinal data and survival models, and we are collaborating with medical doctors from Bordeaux University, but also from beyond, and to develop models and methodologies suited to this kind of data. So today, I'm going to talk about a recent project I've worked on with colleagues, Romain, the use of functional principal component analysis, FPCA, to describe longitudinal data. So the outline of the talk will be the following. First, I will give some notions that you all are familiar with regarding longitudinal data, but it's better to give it again before going into what is functional data. And then I will present the goal of the paper I will talk about, which was to study the robustness of missing data of functional data approaches. So longitudinal data, we are all very familiar with it because in medical study, it's omnipresent, for example, in cognitive aging, in child mental health studies, in prostate cancer, in ICU follow-up, in HIV. In all this kind of context, medical context, we collect many data over visits, over time. All these kind of measures are very different in terms of their nature. They can be like imagery, they can be biological assessment, they can be auto assessment. But the common points of this measure is that they are repeated over times. Challenge because we have great variability across individual trajectories. The measures they are often asynchronous. For example, in a cohort study, you see each and every patient at the same time, so you have asynchronous calendar visits. Also, you can have missing data, and the pattern of the missingness can be and go from missing not at random to missing completely at random, and that will raise different challenges. And also, what we observe, the Xij, I identify the subject and J the measurements, is not, it's a discrete observation of an underlying process, Xi star, that we observe with an observation error. So we do not directly observe the process of interest, we observe discrete measurements with error of this underlying process. The gold standard to model this kind of data is a mixed effect model. For example, one of the most common model is the random slope model. In this model, you have two random effects, one random intercept, one random slope. And the idea of this random effect is that they can capture both the within individual correlation, meaning that two measurements of the same patient will be correlated, but also the heterogeneity between patients. And what B0I here measure is the difference in terms of intercepts for patient I compared to the marginal intercept, the mean intercept at the population level. One big advantage of the mixed effect model is that they benefit from the maximum likelihood estimation theory. That means that you can build some inference tools and you have some convergence results that helps you to build some estimator with good qualities. They can be very flexible also because in this example, I did a very simple mixed model, but if you put some spline in the expression of your model, this can become very flexible, almost semi-parametric, we could say. But often the mixed effect model entails some parametric assumption, whether it is when you use a parametric trajectory, or at least when you specify distribution for the random effect, you have to specify a distribution, often Gaussian, for the random effects. Also, when you have big dimension or complex structure in terms of random effects or nonlinearity, this kind of model becomes very complex to estimate, and that can be very heavy in terms of computational time. So the idea is to dive into other family of approaches, and in particular, functional data approaches. So first, I will give a brief introduction of what is functional data. So I just mentioned this book, which is a data analysis with many useful references and concepts that you can read. At the end, I will also advise another book, which is more helpful when you want to get introductory vision of functional data analysis. So classic functional data looks like this. For example, here we have the height of tangle measured at 31 edges. So it's smooth. We have regular visits over time. And we can have also functional data, for example, in climatology, when you measure precipitation, in this example, each and every day in weather station. And you can see that contrary to what I characterize about longitudinal data, in these cases, we have regular measurements, high density of measure, and no missing data. So this is what classic functional data looks like, because it was mainly developed using sensor data. And this is what you can find when you read Ramsey and the book. You can see that much of the data used classically in functional data analysis was this kind of data. This kind of data is called dense and regular functional data. And if we want to qualify longitudinal data as functional data, we need to change several steps to that. First, we have sparse data, which means that the density of measurement is way less intense. So that's what I illustrated in these plots. But also, the data is irregular. Irregular because asynchronous visits to patients, but also irregular in terms of the length of measure grid, because we can have some missing data for some patient, and the missingness pattern depends among different patients. So the longitudinal data, as I've described it earlier, is what is called sparse and irregular functional data. It's important to know that because many of the classic methods for functional data are suited to dense and irregular functional data, and often they are not very easily applicable to sparse and irregular functional data. So this is important to know when you read some methodological paper or you dive into some packages that do functional data stuff. So what is functional data analysis? It can be seen as a statistical analysis of curves. And by that, I mean that contrary to what we do usually, where we consider observation per observation, in functional data analysis, what is your observation? It's a curve. So basically, we still have observed xij, which are noisy observation of an underlying curve, and the functional data analysis focus on this xi star, the underlying curves, and it aims at making inference on that. And the main idea of functional data analysis is that this underlying curve is seen as a random draw from an unknown underlying function that we aim to approach and to estimate. Some examples of methods that exist in functional data analysis and concepts. You have a functional mean, which is a function, a functional variance, which is also a function. You have the FPCA, which will be the topic of the next slides, the functional principal component analysis. You have also functional linear models, and the variable can be functional, and depending on that, you can have function to scalar linear regression, scalar to function linear regression, and function to function linear regression. And each of these models implies different methodology, different assumption, and different methodologies, because it's not suited for the same stuff. You can also make clustering of functional data, and basically, if you add functional to any stat method that exists, the chance that the functional equivalent exists are very high, because the literature in functional data analysis is quite rich, actually. The focus of today will be functional principal component analysis. So I will give you some insights and concepts about that, and then I will dive into the paper that I was mentioning that studies the robustness of FPCA to missing data. So as you can imagine, the functional principal component analysis is linked to the principal component analysis. In the classic PCA, you have a scatter plot, which is a bit noisy and of big dimension, and you want to project it into a smaller dimension space with an orthogonal basis that maximizes variability. The idea of the FPCA is the same. You have an infinite object, which is a function, and you want to project that infinite object into a lower dimension space to be able to describe the function in a few coordinates rather than a full infinite dimension space. So how does that work? On the that states that the random process that you want to insert, xi star, if you assume that it has a mean function mu and a covariance function g, whose eigendecomposition is the following, then you can write the random process as a sum of the mean function plus an infinite linear combination of some function here, the eigenfunction, and the xi ik, which are the score, the principal. For now, we have a nice expression of the random process as a linear combination, but for now, the linear combination is still infinite. So we did not project anything into a smaller space. So the idea of FPCA, sorry, there is a typo here, it's FPCA, not FCPA. The idea of the FPCA is just to cut and to truncate this decomposition to the first k components, because when you compute the FPCA, the components, as in the PCA, they are sorted by variance of each axis, each dimension. And so by taking only the first k, you take the one that explains the most of the variance. And so in the case of sparse and irregular data, so in the case of longitudinal data, there exists an implementation of the FPCA, which is called the PACE algorithm, that for a given k, a fixed k, gives you the mean estimates over a time grid. The FPC, the functional principal components estimate, which are function over a time grid also. And you have the estimate of the FPC score here, which are the coordinates of one particular individual into this functional subspace. How do you fix k? It's the same as in the PCA. You can fix it a priori by aiming at having only 3 dimensions, for example. But you can also fix that by aiming a certain percentage of variance. And what is nice with the FPCA is that with quite a low k, you can attain quite high percentage of variance explained. And often with longitudinal data, if you have a k with equals to 3 or 4, you can explain at least 95% of the information, which is quite nice. So to illustrate a little bit more what is FPCA, let's say we have some longitudinal data here. So we have some blood pressure measurement for different patients. The FPCA can give you the mean function, which is just the marginal mean function of all this data. You can see that the scale is different. And you have some functional principal components. So each of these is a function that allows you to describe how one particular individual differs when you differs from the mean trajectories. And what you have is that for each of these components and for each participant, for each individual, you have the coordinates. And if you take the linear combination of the mean function plus the FPC times this coordinate, the second FPC and this coordinate, the third and this coordinate, and the fourth and this coordinate, you end up with the estimates trajectory using the FPCA for this individual. And if you switch to the second subject, you have these trajectories. So what is nice is that at the end, what you have is time-independent feature. For example, if you want to use longitudinal data into a model, you can just sum it up using the FPCA and using the scores, and you get some time-independent feature, and so you can do more stuff. For example, if you want to cluster some longitudinal trajectory, you can do the clustering directly on this score. So what you need to recall that these coordinates, these scores, you can see them as coordinates into a functional space, functional subspace, sorry, of low dimension that explain most of the variability of the longitudinal data. So from that, a parallel can be drawn between FPCA and mixed model. And the score in particular, they can be seen as a kind of random effects. And then the number of FPC is the number of random effects. And the mean function is the equivalent of the marginal mean. The difference between the two methods is that the mixed model is parametric because you have to specify a trajectory and a distribution for the random effects, while the FPCA is non-parametric. It just implies a smoothing based on some spline basis in the background, but it's non-parametric. The drawback of that is that you don't have inference tool, at least directly, using the FPCA, while in the mixed model, you have all the inference tools you are familiar with, and I mentioned earlier. And a thing that was not clear at the time we dive into this method, it was the robustness of FPCA to missing at random data and to missing data in general, while for mixed model, it is known that it's quite robust to missing at random data. So this was the goal of the paper that I will now present and the work we did on that. So what we did is that we built 2 different simulation studies, and I will introduce you this simulation study. At the end, I will give you some short real data application, and then I will try to explain you why we wanted to do that and what was the motivation, because we were planning to build some model afterwards. So the first simulation study, the aim was to evaluate the robustness of FPCA to dropout. So we focus on dropout because it's a very common type of missingness pattern in core data, and we work a lot on core data, but the results can be generalized to intermittent missing data. And in fact, dropout is actually a more complex missingness pattern because from the time of dropout, you lose every information for the subject. So we generated a trajectory for many patients. Some of them were used for training the model and the other one to evaluate the model. We simulated one measure every year up to 12 years, and we had different intensities of dropouts and different type of missingness scenario. There are way more scenarios in the paper. For the slides, I only show a few of them because it will take too long. So I have a missing at random scenario and a missing not at random scenario. Why I put a missing not at random scenario? Because we do not expect good performance in this case. And in this case, actually, only a joint model that models the missingness pattern can perform well. In this first simulation study, the estimate was, the idea was to find, for all the missing observation, we wanted to rebuild the trajectory using the FPCA and to build this missing observation, and we compare the predicted observation to the one that were missing, because we know the true value because we simulated them. So the methods and the models used in this simulation study, we had linear mixed model with cubic trend or spline trend with nodes at the quantiles. We have a joint model for missing not at random only because it's the gold standard in this case. And for the FPCA, we have chosen a FPCA and 2 different implementations, one which aims 90% of variance explained, and one where the K was fixed as 4. That means that we have 4 dimensions in the functional subspace in this case. And how do did we evaluate the performance? We choose the RMSE only for the missing observation, and to be able to compare between models, we choose a relative RMSE, and by relative I mean that we took the raw RMSE over a RMSE of a flexible model that has been estimated on the complete data over 1,000 replicates. So the generated data looks like that. Here we have the complete data, and then we add different type of missing data in green that labels the visits, the last visit for the subject, which is its dropouts. So in black, it's still the complete data. I just added the simulated time of dropout for each and every individual in green. In yellow, it's when it's administrative censoring, which means that this participant will be followed up on all the time window. And you can see that this fixed scenario is very particular because basically whenever a patient has a value above a certain threshold, it's considered as dropout. So it's a very harsh scenario, not very realistic, but we wanted to try and to evaluate the FPCA in this context also. These two are more realistic. We have increasing probability of dropout with time and increasing probability of dropout with time, but this time missing not at random. That means that it also depends on unobserved measurements. And so in this case, mixed model doesn't work well, and we wanted to evaluate how FPCA was working in this case also. So here are the results. So how do we analyze this result? So in the first line here, you have the scenario with 30% of dropouts, and in the second line, you have the scenario with 60% of dropouts. Here you have the fixed dropout scenario, and here you have the increasing dropout scenario, missing at random, and here missing not at random. You can see it's missing not at random because we have the joint models that appear there. What is important when you compare the results is that you can compare the box plot inside one pane, but you cannot compare the box plots between pane because the relative RMSE is computed inside the pane. So it's relative between all of them compared to the best model inside this scenario, and this scenario, okay? So in the fixed dropouts missing at random scenario, what we observed is that the performance of the FPCA here there seems to be better, and here they're similar, let's say, apart from this one that performs better. But again, this scenario is not the most realistic. What is more interesting is to look at this scenario, and in this case, we have a dropout that increases with Y. And actually, in this case, we can see that when the dropout is at 30%, FPCA performs slightly better than the linear mixed model. And when we have a 60% dropout, the performance are quite similar. On the contrary, when you have missing not at random, you can see that with reduced dropouts, they all perform quite similarly. But when the dropout increases, the joint model seems to perform better, while this one also has nice result. But in this case, at least the FPCA doesn't perform well. But that was kind of expected because what we aim is to have robustness to missing at random scenario more than missing not at random scenario, which is way more complex to model and to take into account. So that's the first simulation study. Now I will go into the second simulation study. The aim was still the same. We wanted to evaluate the robustness of FPCA to dropout, but this time we generated the data a bit differently. The setting is still the same. We generate a longitudinal trajectory for different patients with one measure every year up to 12, different intensity of dropouts, and only a MAR scenario in this case, at least in the slide. There are more scenarios again in the paper. And how do we generate the data? In this case, we took the simulated data from the first simulation study, and from that, we run an FPCA here with only two components. So we have the mean function here in the top, and the two functional principal components here. And what we did is that we randomly sample scores using a Gaussian distribution. And by taking the linear combination of the mean function, of the randomly sampled score, and the functional principal components, we get the simulated observation. Also, we included an observation error here. So the Xij are our simulated data, and from that, we added some missingness. Okay, and so in this case, the goal was to estimate the original mean function and functional principal components to see if, even with missing data, we were able to retrieve the mean function and FPC that were used to generate the data. In the result that I'm going to show you, we have only used FPC with k equals 2, because it's the value that was used to generate the data. And in this case, we use as performance measure relative bias that compares the true versus the estimated function, because all the estimates are functions, over a fixed time grid for 1,000 replicates. So this is what we get. So the same thing are plotted. So here you have like some randomly sampled estimates with the truth in black, and here you have the relative bias in the left box plots. What you can see is that when the dropout is small at 0.3, the performance of the FPCA to retrieve the mean function is correct, but it deteriorates the further we are from the origin, and that's because of dropout, we lose some data at the end, and we have fewer and fewer data on this part of the time window. So that's why the FPCA deteriorates. Regarding the functional principal components, we can see that the performance are quite correct, and the intensity of dropout doesn't change much the quality of the estimates. And you can see that in the box plot, but you can see it better there, that overall, all estimates are around the true value, and you still have problem on the bounds, but that's linked to the way internally the FPCA estimate the functional principal components. There are some smoothing based on spline behind that, and depending on the constraints you put on the splines, you can have this kind of pattern on the margin. So now let's dive quickly into the real data application. So we used some core data from the 3-city study, which is a study that follow elderly people to assess their cognitive aging. And from this core data, we built a nested case control study. We took the incident cases of dementia, and for each of these cases, we matched one control that at the time of dementia of the cases had the same ages, same sex, same diploma level, and the same length of follow-up. And we match them, and then we estimate for all this data, the nested case control data, one FPCA and one linear mixed model with cubic spline to see if the estimated trajectory were comparable. And what we get was that, so for 4 different cognitive scores, the BVRT, the IST, the MMS, and the TMTA, we have this kind of data. So in green, you have the FPCA for the cases in solid line and for the control in dashed line. And you can see that the estimates are quite similar, even though in the FPCA, it's more, it's less smooth. But that again is linked to the way the FPCA is internally handled, because it's based on some spline decomposition, and depending on the choice of the spline, you can have this kind of data. Also, this is even more true for TMTA, but this is because in the data we had way more missing value for TMTA and even some patients that are not any value, so we don't have all of the participants in this graph. But you can see that for the BVRT of the MMS or even the IST, for which we had more measurements, the trajectory are quite similar. Okay, so I might have been a bit quick, but it might sound done, so feel free to ask questions afterwards. But in the paper, I describe more thoroughly the FPCA and the comparison to mixed effect models. And I have way more scenario with different patterns of missing data, different ethnicities, and I give the result for each of them in the supplementary also because that will mean too much plot in the paper. And you can also find the code. I didn't check the QR code. I don't know if they're still updating. If not, feel free to tell me and I will send you updated links. And I have put all the simulation code in my GitHub account. So if you want to have a look into the code to see how I've estimated the FPC, how I've generated the data, you can have all of that both in the paper because I describe the generative algorithm, but also directly in the code, in our code. The take-home message that I think is important regarding FPCA is that FPCA can be considered as a flexible non-parametric descriptive tool for longitudinal data. And the conclusion of this empirical simulation study is that FPCA seems to be robust to missing at random data, as long as you are not in pathological missingness case, because obviously if you don't have any information on some area or some time window, FPCA won't be able to retrieve this information alone. And to me, what I find is one of the main attraction of FPCA is that from longitudinal data, you extract the FPCA score that characterizes the temporal data as time-independent features. And for example, from that, you can do many interesting stuff. And what I'm currently working on is that if you want to do dynamic survival prediction using longitudinal data as input, you can do two-step approaches by doing first an FPCA that will estimate the scores of each and every individual trajectory. And then you can feed this score into any model that survival model that can make dynamic predictions. So it can be a Cox model or more complex joint model. So there are many possible directions from that. I mentioned also clustering. And indeed, I have a student that works on clustering longitudinal trajectory using FPCA score, and it works quite well. So these scores and the FPCA interest doesn't lie only on the flexible non-parametric description, but also on the fact that you can extract some features of time-dependent data that becomes time-independent. So here are some key references. So the book, the first one is the one I've already mentioned, and the second one, more recent and more introductory, is a nice read, in my opinion, because it gives most of the concept and notion that you can find on the functional data analysis, but in a more friendly way, and it's easier to read as a statistician and as an applied statistician. One main reference to me regarding this project was a Yao paper, which introduced a PACE algorithm that allows to estimate the FPCA with longitudinal data. It's not necessarily an easy read, but there are a lot of discussion and paper that discuss that. And I think in the Kokoska book, they mention the PACE algorithm, so you don't necessarily need to read this paper. I've also put some packages here that make functional data analysis in R. The more classical is FDA, which is based and done by Ramsey team, but it's more suited to dense and regular functional data, and it's actually quite complex to use. But if you want to use FPCA with sparse and irregular functional data, EHUB with longitudinal data, I would advise these two packages, FACE or FDA PACE, that differs only on the way that internally the smoothing is done. It's not the same spline basis that they use. And you have also the package fun data, which is more general and that allows you to have some plotting and representation, nice representation for functional data in shape of matrix and etc. Thanks for your attention, and feel free if you have any question or if you need any precision regarding what I've said.